All right, everyone see the screen?
Yep.
Yes, sir.
Okay. This is our 16th lesson on the flood. And this is from my book, The Study of the Biblical Flood. And this is from the second edition of it, which nobody has a printed copy of because there's not one in existence yet. I'll try to print it later. But I want to try to finish it up and get the second edition in place to be printed. And when we look at this, we talked about isotopes last week. Now the word isos, and put a sigma right here. Can you see it?
Yes.
Okay.
Yes, sir.
Okay, so isotope, isos, is the Greek word for same. And so what we have here, isotope of hydrogen, this is just hydrogen. It's depicting what an isotope is. To make it hydrogen, to make it the element hydrogen, it has to have one proton in the nucleus. Now, if the atom is not excited in some way, ionized, it'll have one electron. But we don't really worry about the electrons. We're looking at the protons. That what determines the element. Now, at first, when they were separating the elements out, they thought that these different isotopes were different elements. So they gave them names. So hydrogen, the isotopes of hydrogen have a name for them. The other isotopes don't have names. I don't know of any that do. James, do you know of any other isotopes that have names other than hydrogen?
No, I do not.
Okay. So what we have here is the main isotope of hydrogen. Most hydrogen atoms, the vast majority of them, and you can get into your physics books and they'll tell you what percent of them have this, but a very high percent of them, probably well over 99% of them, would have one proton and for hydrogen, of course, one electron normally, thus they're ionized, one proton, and then there'll be one particle in the nucleus. So this is the number of protons. This, you see my cursor, and right here is the number of particles in the nucleus. Now, most of your hydrogen atoms that's what they are. Deuterium, duet is 2, see, deuterium. That looks like a Latin word, probably is. The IUM is, I think, a Latin ending. But a duet is 2, so we still have one proton. That's what makes it hydrogen. But it has 2 particles now in its nucleus. And one of these is a proton, the other is a neutron. I'm trying to move my cursor around so you can see it. So this is, it's almost exactly twice as heavy as the main isotope of hydrogen, regular hydrogen. Now then, we have tritium. Tritium has one particle in the nucleus, one proton in the nucleus. That makes it hydrogen. Then it has 3 particles in the nucleus. So it has 3. That's where this 3 is. So we have 1 proton and 2 neutrons. It's still hydrogen because it only has 1 proton. Now then, are there questions about what an isotope is? Chemically, okay, you had a question, somebody, or comment? Chemically, hydrogen, this isotope of hydrogen will mix with water and give you H2O. There'll be 2 hydrogen atoms and 1 oxygen atom will make water, H2O. And we could also take deuterium and it'll also mix with hydrogen and form water. But what we have is it'll have 2 extra neutrons because they have two atoms. So there'll be 2 more neutrons in that water. So the water is going to weigh more than the water made with protium. And so it will weigh more than this right here. Now, if we have tritium and it mixes with oxygen, it will also make water, and it would have 2 extra neutrons, 2 extra particles of the nucleus for each of those atoms. So it would have 4 extra neutrons in it. for the water, for the molecule of water. So it's going to weigh more. Each one will weigh more. The molecule will have more mass or more weight. Any question there? All right. Now, this is going back to something we covered last week, and I want to illustrate and show you how they do something. Let's look at oxygen. Now, they looked at the oxygen isotopes in the fossils in order to determine some things about it. We're going to show how that works. Okay. Normal oxygen has 8 protons in the nucleus, and it has 16 particles in the nucleus, which means it has 8 protons and 8 more particles, 8 protons. I'm sorry, I said neutrons. 8 protons in the nucleus, and it would have 16 particles. So it would be 8 protons plus 8 more, which would be 8 more neutrons. So it has 8 protons and 8 neutrons in its nucleus. This is a stable isotope of oxygen. It won't decay radioactively. There also is an O817. This still is oxygen, but because it has 8 protons in the nucleus, but it has 17 particles in the nucleus instead of 16 like the normal one does. Most oxygen atoms have just 16 particles in the nucleus, 8 protons, 8 neutrons. This isotope has 8 protons right here, but it has an extra neutron, making it 9. So it has 9 neutrons and 8 protons in its nucleus. So it's still oxygen because it has 8 protons. Now, over here, we have another isotope, and this is stable also. It has 8 protons, making it oxygen, but it has 18 particles in the nucleus. So it has 8 protons in the nucleus plus 10 neutrons in the nucleus. Now, does everyone see any questions about that? Now, last week I was mentioning it, and I said I used the word. I listened to it later, and I used the word neutron instead of proton one time. Got it backwards. I'm sorry about that. Okay. So, all right. Any questions? All right. Right here, I picked this off a website. Here is the light H2O. Now, that would be 16. That would be your 16. Now, when they evaporate, what happens with evaporation is the molecule has to get moving fast enough to come out of the surface as a vapor from the surface of the water. The heavier the molecule is, the more energy it has to get to exit the water. So the 16H, with oxygen with 16, isotope 16, let's go back to it. With O16, this small, lighter isotope will evaporate quicker as water, quicker than with the 18. So it's heavier. The 18 is heavier than the 16. And so the 16 will evaporate more. So it will go up into the clouds and wind up down here. And so the 18 will tend to stay in the water longer, and less of it will come out. And so they say in the non-glacial period, you'll get the light H2O. It'll have this 16 in it, not as much 18. During the glacial period, seawater is enriched in the heavy H2O. That's with its 18 in it. Glacial ice is with the lighter H2O. That's their claim. Does that make sense? And so they look at the amount of the isotopes, different isotopes of oxygen, to tell how old it is, right? Based upon that. And that's what we had here. All right. Any questions? We go back to this, and right here, Gary Landis in the U.S. Geological Survey measured oxygen in microscopic air bubbles trapped in amber, a fossilized tree resin. He found the amount of oxygen dropped from 35% 2 million years ago before the end of the Cretaceous period today to the oxygen level of 21. It dropped down. Now, here's the thing. The oxygen appears from this, and there's one other source, to have been 35% oxygen rather than the present 21%. Now, the more oxygen's in the air, if you get too much oxygen, it becomes toxic. It'll kill you. But if you don't have enough, you can die from that too. But having 35% won't kill you. Okay. So that's not the point where it becomes toxic. So we have a 21% now and a 35%. Now, what would this do for us? If our atmosphere had 35% oxygen right now instead of 21%, it would be easier to breathe. And your breath, your lungs would not have to work as hard to breathe if that were the case. Now, if your respiration rate slowed down, it would mean that you wouldn't work your lungs as hard. So that would, of course, I believe, create a situation where your body is not working as hard. You probably would live longer. Any questions or comments? But this is scientific evidence that it was 35% in the past. Now, right here, this is another one from another source, from another piece of information. This is Graham. The recently developed oxygen model of Burner and Canfield confirms general features of several earlier reconstructions and indicates a rise in oxygen to 35% and then a fall to 15% over the span of 120 million years. So they're claiming it went down to 15% at one time. Well, that would be pretty hard to live and breathe in during the later Paleozoic. But the source, they got 35%. Now, that's the same figure we got up here with Hecht. He got 35% with some other piece of information. So we got two pieces of information that has it 35% in the past at one time. Are there questions? Burner has the oxygen level about 39%. This is another source. Well, 39 and 35 are pretty close to one another. That's 290 million years ago, according to their model. Now, I don't have the graph from his book in the slides here, but that's the book side here. I haven't included in this presentation. Now, so we have three different sources that are all pretty much the same. Two of them are 35%, one is 39% oxygen, which would change how we breathe. People who are having breathing problems will add oxygen, and they'll put more oxygen, and they'll put oxygen in their nostrils to help them breathe better. People who are having heart trouble and other problems. In global climate models, nearly half of the projected increase in temperature due to the doubling of carbon dioxide in the atmosphere results from the effects of increased water vapor. A doubling of water vapor in the stratosphere would lead to a 1 degree Celsius increase in surface temperature, according to Altman and Hoffman. That's what they claim, 1 degree Celsius. Now, that's not a whole lot, 1 degree Celsius. But if you put it all over the world, it would affect things. However, the problem that they have here is I've looked at this and found some other sources, and they really don't know that this is true, because the problem is the increased water vapor blocks out other light from coming to the earth. Now, the water vapor will not allow the light from heat, that's called infrared light, to go through it. It's opaque to it. And so what we get is it would block the infrared light from coming into the earth from the sun even. So when you block it from coming in, you don't get that added heat. Now, other light comes in, visible light comes through water vapor. It's transparent to it. And some of your ultraviolet light is blocked by water vapor. So more water vapor blocks other light from coming in. It does keep the heat in the atmosphere, but it doesn't allow as much to come in as energy to come in. So if you reduce the incoming energy, you can retain more of the energy and still not have a runaway greenhouse effect. Any questions or comments there? Again, I'll get the cite on this. It's in the book, and I do cite it in the book. Okay, I think I have it in my notes here, but I'll make sure it's in next week's notes if it's not in this week's notes. All right, the present radiative forcing from the estimated rise in stratospheric water vapor resulting from methane oxidation is calculated to be about 10% of that of CO2. But right here, this is what I was talking about, but our limited knowledge of water vapor in the upper troposphere and lower stratosphere is one of the main uncertainties in climate modeling. In other words, we don't know what it's going to do. But let me say this, we know it doesn't let infrared light come through. So light that's coming from the sun that's infrared light, which is heat, would not come through the atmosphere. It would be blocked by the atmosphere, by the water vapor. But heat won't get out of the atmosphere either as readily. Can't get out either. So it keeps it in. Now then, if you reduce the amount of heat coming in and you keep heat in, the uncertainty is, how is the other light coming in, which can be converted into heat, how is it going to affect the net amount of heat in the atmosphere, amount of energy from heat in the atmosphere? Again, that's what he's saying here. It's an uncertainty. That's Olsman and Hoffman. That's what I was referring to just a moment ago. Questions or comments? There are models that can't figure out exactly this. There's too much uncertainty because it blocks some light from coming in and let other light come through. So we'd have to know how much energy is coming from those other sources of light. And then we'd have to know the reflectivity of the surface. That's called albedo. There's several factors that come into this matter. Okay. All right. Now, energy can be converted into heat, but it can also be converted into growth of plants as well and animals. So that right there is another factor. Any claim by atheists that there were extensive amounts of carbon dioxide in the atmosphere is untenable. Now, let's look at this, and I believe it's untenable. This claim is untenable because it would cause a runaway greenhouse effect, which would preclude the existence of life on Earth. So if we have too much carbon dioxide, it also has a greenhouse effect. Now, there's another problem with the greenhouse effect that they don't even factor in, and this is methane gas. Now, methane gas comes out of the surface of the Earth through tiny cracks in the Earth, and the natural gas that they worry about burning and everything, it's converted to carbon dioxide when they burn it. But methane is something like 10 times more potent greenhouse gas than carbon dioxide. Again, the people who are worried about global warming don't factor in all of the other problems they have. If we don't burn the natural gas, we let it seep up through the Earth. It comes through the crust of the Earth and comes up and moves up into the atmosphere. And they can measure it with some of their satellites. And they scan the Earth for different colors of radiation. By radiation, I mean light, and various kinds of colors of light. And that would be ultraviolet and visible and infrared and so forth, all of those bands of spectrum of light. And they can find where natural gas is coming up through the Earth itself, coming out of the rocks, coming out of the top through the soil. And then this methane then is much more potent than carbon dioxide. So if it were burning it instead of letting it seep up through the ground, that would actually affect the greenhouse effect. and reduce it, in fact, rather than increase it. Because remember, methane is more potent as a greenhouse gas. Any questions? There's too much CO2 for organic microevolution to occur if we have a runaway greenhouse effect. It gets too hot. Some estimates project that if all the CO2 locked in the carbonate rocks were released, the surface atmospheric pressure would become 60 times higher, rivaling Venus's thick shroud, according to Sky and Telescope. This is not a scholarly journal, but this is a journal that does publish a lot of material. Okay. All right. Any questions? So we got a problem. The atheist has a problem if he gets all that carbon dioxide if it gets too hot. Now, I want to explain where the carbon dioxide went to and where it came from. In 1986, later I'll do it, James F. Casting and Thomas B. Ackerman in NASA's Ames Research Center studied climate models of an atmosphere with high levels of carbon dioxide, CO2, carbon dioxide. They concluded that with 10 to 20 times more CO2, carbon dioxide, than in our present atmosphere, surface temperatures may have soared to 85 degrees Celsius. Now that's 185 degrees Fahrenheit. I guarantee you that will kill that'll kill most life. They found some life forms that can survive that temperature, but not very many. The high temperature could have been detrimental to burgeoning life, and that's what they're saying here. These people are atheists. They think it evolved. So that's a problem for them, and they admit it. With an atmosphere containing large amount of carbon dioxide, the temperature of their surface would have exceeded the value, which would allow the value, by that I mean the temperature value, which would allow the formation of organic molecules. Too hot. Gets too hot, the organic molecules will break apart. The molecular bonds will be destroyed. The atheist has a problem in that he has to remove the carbon dioxide, CO2, from the atmosphere to have life to evolve, but he can't remove it without living organisms. Okay, living organisms are the very things that remove it. Plants remove the carbon dioxide and store it in their stems and in their leaves, and they put it down into the ground with their roots. And so they've actually put it down into the ground. And so what we have here is you got to have living organisms to remove the carbon dioxide, but you can't even get them to evolve without, if the carbon dioxide is there, it can't evolve. It's too hot. Again, I think they're in the catch-22 situation, the atheists are. Either the temperature of the Earth's atmosphere was too high for life to evolve, or the limestone, coal, etc., were not of organic origin, because that's where a lot of your carbon dioxide is stored. Your carbon is stored, say, in the limestone, coal, and other sources, in the fossils. Or the organisms were created with the carbon cycle in balance, and the limestone, coal, etc., were deposited during the flood. Oh, the third option is the one I believe is correct. That's the correct option. The other two just won't work. It's too hot for life to evolve, and you can't get rid of it without the life. You can't have it. You can't get rid of it. See? So that's the problem that they have. Any questions or comments? A water vapor canopy which probably existed above the Earth prior to the flood, would hold the temperature relatively constant at a temperature, I'm arguing, around 75 degrees Fahrenheit, about 23.9 degrees Celsius. Even atheists agree with this point. Remember, we've already quoted and shown that they argue that this was about the temperature of Earth's atmosphere in the past. So they can't say it couldn't happen because they've already claimed that it did happen. So if they claimed it already has happened in the past, then we can postulate that it did happen during the flood or before the flood, antediluvian world. They agree with this point, as we've already laid out. It's evident the temperature was about 75 to 80 degrees Fahrenheit, 23.9 to 26.7 degrees Celsius. because of the presence of tropical and subtropical plants under the Arctic ice caps, according to Francis, pages 56 to 70 to 62. Now, Francis is a man's last name, not a person's first name. At temperatures of about 85 degrees Fahrenheit, these plants thrive. They actually thrive. Some of these tropical and subtropical plants that they find in Greenland. Okay. In Axel Heiberg Island, that's an island up in the Arctic Ocean in northern Canada. It's a Canadian island. The forests are mummified. There are forests there that are mummified. Now, what would mummify something? Well, if you have the water to evaporate out of the wood, it would mummify it. Now, how can you get it out? Now, we talked about the 4 states of matter last class. Let's go back through and review them. There's solid. Now, water exists as a solid. We call that ice. There's a liquid. We call that just water. Then we call it a vapor. That's water vapor. Now, then we have the 5th state is plasma, and I think my figures are that if it got hot enough to form a plasma, it would break down the H2O molecule, and it would break it apart, and so it would not be water. Actually, it'd be back to hydrogen and oxygen atoms. But if that's the case, what we have here, we can go from, by heating up ice, we can melt it and make it into water. We get it even hotter and make it go into a vapor state. But when we get to the molecular level, one atom or molecule at a time, there can be situations where one molecule will get enough energy, kinetic energy, to evaporate. That is from ice. So ice can go directly to a vapor state without going to the liquid state. That's called sublimation. Now you see that in freezer burn in your refrigerator or your freezer. If you have a deep freeze of some sort of freezer in your refrigerator, it's called freezer burn. What's happened is a few of those molecules then radiate out and get enough energy, and they fly out and leave the meat or whatever it is that we had. You can actually see freezer burn if you'll get a little bag and put a couple of ice cubes in it. One of these Ziploc bags, and put a couple of ice cubes in it, and then look at the size of the ice cubes, or just get one ice cube and put it in your freezer, and just leave it come back about 2 or 3 months later. You'll find that a lot of that ice will wind up on the inside of the freezer itself, or you just leave an ice cube just sitting out without being in a bag. And what'll happen is it'll just evaporate away and it'll be gone. And it'll look like it has holes in it at first, but it'll evaporate. So it sublimates. That's called sublimation. It goes from a solid to a gaseous state without going to the liquid. Now here's what happens. These forests are mummified probably through sublimation. The wood is dry and somewhat compressed, but otherwise unchanged. Now the compressing of the wood, I believe, we're going to explain that later. But the dryness of the wood, if it was extremely cold, it could sublimate and it's like freezer burn, what we call freezer burn. But otherwise, for many trees reach more than 100 feet in length. So these trees were 100 foot tall up in what is now the tundra, and places up in Axel Heiberg Island, which is up in the Arctic Ocean. 100 foot tall trees. That's a pretty tall tree. Axel Heiberg Island is only 680 miles or 1,100 kilometers from the geographic North Pole. That's pretty far north. Right? Any questions or comments? Here's where Axel Heiberg Island is. Here's the United States. There's the state of Alaska. There's the island of Greenland. I believe that's Iceland over here. And there is Axel Heiberg Island. The red right there is Axel Heiberg Island. Here's Chicago, Illinois is right in here. Let me see. Lake Michigan. It's down below here. This is Minnesota, and up here, North Dakota, Canada here. Any questions about that? That's pretty far north to have 100-foot tall trees. Here's a picture from space of Axel Heiberg Island, and that's what it looks like from space. Here's another picture of Axel Heiberg, best shot I could get of it. Doesn't look like much is growing there now, but there's a lot of soil and rocks and so forth. Here's a tree stump, a fossilized tree in Axel Heiberg Island. Tree that's fossilized, right? There's some fossilized tree branches. That's some of they were fossilized. They were actually frozen. Cypress needles. These are cypress trees in Axel Heiberg Island, okay? The fossil remains from Axel Heiberg Island are an outstanding example of preservation. These plants are not permanentalized, replaced with silica. Now, but if you've ever seen what's called petrified wood, that's permanentalized. They've replaced the wood has been replaced with other materials, silica being one of the things that they replace it with. I have pictures of some petrified trees out in Arizona that I have. We'll show them. They still contain their original carbon-based material, and the wood from the trees can still be burned. Okay, so they can still burn the wood. So right here, it's not petrified like we think of petrified wood. Now, petrification, they used to say took millions of years, but now there are people that can petrify things for you, and they can do it in a month or so. And so petrification can be done quickly, just like creating oil and coal, as we've already shown. The picture to the left is an example of the outstanding preservation. These cypress needles, now let's go back here. That's your cypress needles that we have here. And I'm just getting a quote of this. That's what they're looking at, is an example of the outstanding preservation. These cypress needles found in a forest floor. Now, this is a quote right out of this article that I'm citing. These cypress needles found in the forest floor litter portion of the Axel Heiberg Island deposits are over 40 million years old. That's their dating of it. Because the incredible way they were preserved, they look better than most year-old forest floor litter. So it's 40 million years old, but it looks better than 1-year-old forest litter. Okay, interesting. I find that interesting, amusing almost. All right. These flora, now fauna and flora, fauna is animals and flora is plants, are not permanentalized. That is, they're not made into fossilized wood. So we have, because of the way they were buried, while they were still living in the Eocene, the forests were covered by silt-filled floodwaters. Interesting. The silt blocked out the mineral-rich water and protected the flora from being replaced with the silica in the water. That's their claim. I think they've missed it, but we'll get to it later, okay? These great floods, now they're talking about the floods that caused this, were not a yearly occurrence. Instead, they occurred perhaps every 10,000 years, okay? So here's something that occurs on a 10,000-year cycle. It was this flooding that preserved what the forest was like. The forest was like and the 100-foot tall trees and so forth, and the leaves, and the pine needles, the cypress needles. After the floods, a new forest would grow on top of the old one. There are at least 19 such events on Axel Heiberg Island. Now then, so they say we have these layers, and there's another layer on top, and a layer on top of that. And so they say there were at least 19 such events. My model explains this without having to reject the flood, okay? But some models have trouble with it, okay? My model doesn't. The evidence of multiple floods is that the fossil trees are in successive layers of sediment. The flood model developed in this study explains these successive layers of sediment with one flood. And we'll describe the flood as we go through, show it. Any questions so far? If there were 19 new forests that grew above each other, how was the wood preserved? I got a question for you. How was it preserved then? Should not have been preserved. Good. The notes on the prior slides were obtained from the following website. Now, this is the Hooper Museum, and there's a link to it. If you're watching it on the internet, you can pause it and find this website. Some of this information was derived from websites that were certainly not friendly to the flood model. In other words, they were written by atheists and they don't believe in the biblical flood. Keep that in mind. They're not friendly to a young earth model either, as well. All right. They're reluctant witnesses. Now, there's three kinds of witnesses when you're trying to prove something. There are friendly witnesses, and those witnesses can be tainted, or the people can accuse them of being biased. Then there's opposed witnesses. This is someone who doesn't agree with you, what you're saying, but they'll testify that what you're saying is right. Now, that's called a reluctant witness. Then there's a witness that is not concerned one way or the other. So these are your three kinds of witnesses if you have a courtroom or to decide something to. So these are reluctant witnesses. And in fact, when the enemy admits that you have the truth on something, that's pretty strong evidence that you have the truth on it. Okay. So we have reluctant witnesses. Here are some fossilized trees from Heiberg Island. Now notice these are not petrified wood. Keep that in mind. These are actual trees. This is actual wood that will burn if they burn it. I hope they're not trying to burn it, but I think they've taken some pieces of it and shown that it does burn. So it is still wood. It's just lost. It's lost its liquid in it, and it got so cold. I think it was due to sublimation. A little bit compacted. Now we're going to show why it would be compacted and old, and the other sources of information that I'll have part of the mechanism. Studies have been done comparing the modern analogies of these fossilized plants. The climates that they lived in gives a clue the climates of the Eocene. That's the claim. The trees from Axel Heiberg do not have any late wood, which is common in modern trees. It indicates a dormancy response brought on by low winter temperature. The fossil trees do not have having late wood, and another clue indicating mild temperatures even in the 6 months of winter. So what we have is we don't have the cycle like we have in our trees in Oklahoma. It gets cold in the winter and the trees become dormant. So we have the growth is cyclic. It cycles every year due to the change in temperature. But we don't have this here. So we have a situation that's entirely different. We don't have the cycles of our trees that like they have now, and particularly in the colder regions of the earth. As well as having 6 months of darkness, that's what they claim on this website. These trees also had 6 months of solid daylight, and they claim they adapted this with fast uninterrupted growth. The fossil log in the picture was most likely knocked over during flooding and then buried. Some of those knocked over logs can be up to 8 meters long. Now, a meter is about 3.37 inches, or about 3.28 feet. So just mark that by 3.28, and you'll get how many feet it was. So if we take 8 times 3.28, we'll get about 26 and a quarter feet roughly. That logs are that long. Okay, that's still fairly tall. Okay. Questions or comments? Now, I want to stop here and see if you have any questions about this. Anybody got any questions?
What does that mean for tree rings?
Well, because you don't have the dormancy period, you still would have tree rings, but they wouldn't be as pronounced as they are now, because it would be a cycle that would be there would be some period of growth, a little bit of growth, but not as much. So you would have some tree rings. You would have tree rings.
Okay.
They get tree rings, I believe, in these tropical regions where it goes through cycles. The cycles of growth might be due to the change in the amount of moisture. So if the tree doesn't get as much moisture, its growth slows down. What trees do whenever they get too dry, they'll start shedding their leaves. So they kind of go into a dormancy like that, and they shed their leaves, or they drop some of their leaves. We have a sycamore tree in our front yard, and when it gets real dry in the summertime, it'll start shedding leaves. It won't shed all of them, but it'll shed some of them because it's trying to protect itself. Too many leaves will pull too much moisture out to make the plant food. So yeah, I believe there still would be some tree rings. Okay,
Thank you.
but that would not be as pronounced as they are with the full cycles that we have in the winter, where it becomes totally dormant. Okay. Any other questions or comments? I thought of something else I need to bring up there, and is that we have with Axel Heiberg with this 19 layers. That's kind of important because we're going to get other sites that have multiple layers as well. So these have to be explained, but some of the flood models that I've dealt with don't explain them. Now, a problem that they're claiming, there was 6 months of winter that far north. It's north of the Arctic Circle, and so the tilt of the Earth on its axis creates a situation where you do have times where you don't have any sunlight. However, if we had the water vapor canopy, we'd still get heat from it, which is a form of light, and the trees might even still continue to grow if they had the infrared light. So infrared could cause them to continue to grow. Any questions or comments there?
With 19 layers and the cycle being 10,000 years, you've got 190,000 years, but yet this extended over a much greater period of time.
That's their claim.
It just seems like too few layers in a sense.
Yeah. But I think the 19 layers is pretty easy to explain whenever we get to my flood model. Okay.
Okay.
I don't have a problem with it. But my flood model has 3 mechanisms, as I said last week. We have the 40 days of rain, 150 days of breaking up of the fountains of the deep, and 150 days of the windows of heaven. Okay. So the rain stopped, and 110 days later, then the fountains of the deep and the windows of heaven stopped. Both of those continued 150 days, if you'll get into the text and read it carefully. So I think that we have 3 mechanisms here, and these mechanisms, I believe, will help us to explain everything that happened. Now, let's go back one other thing here now. 35% oxygen would slow down the respiration rate and slow down the heart rate. Because if your respiration slows down, your heart doesn't have to beat as fast. If you're getting more oxygen into your blood quicker, your heart rate slows down. That's what happens with athletes. If they work real hard, they become more efficient at it. And so this would change the longevity of mankind and animals as well. Change how long they live, because they don't have to work as hard to breathe, and that slows down their pulse rate. And your heart doesn't have to work as hard to pump blood through the system to get the oxygen to your cells. Any questions or comments? We are pretty close to where I want to stop. I wanted to make sure that we understood the isotopes and how this worked. And I'm going to go back to the isotopes one quick time, just to talk about it just quickly because we got just a few minutes to do that. Isotopes of hydrogen, different number of protons make it a different element. But if you have the same number of protons, it's the same element. And even if you have more neutrons, it's still with the same number of protons, it's still hydrogen in this case. Same thing happens with oxygen. So let's just take oxygen. We'd have 8 protons in here, and 8 here, and 8 here. We'd have 8 protons and 8 neutrons. That would be the most stable isotope, most common isotope of oxygen. Then we'd have 8 protons and 9 neutrons over here for the second isotope, and then 8 protons and 10 neutrons for oxygen. Now then, this oxygen, these 3 isotopes, what we get is this water here, this glacial ice, has a lighter H2O in it, and the seawater has a higher level of it. So sea creatures, fish and so forth, fossils, are going to have more of the oxygen 18 isotope, which will have 10 neutrons and 8 protons in the nucleus. So they're going to have more of that. That's how they come up with this view about the temperature, the temperature being what it was, what they claim it to be. And that's probably pretty good evidence. Are there questions about that? Most of your atoms have different isotopes, and some isotopes are radioactive. They'll break down with time. And we're going to get into that in the next lesson or two. We're going to go through carbon-14 dating. We're going through that. So I'm going to call a halt to it right now. It's about the point of quitting. We didn't quite go an hour, but we went enough to cover the material. Any questions or comments? Okay.